Hello everyone, thank you for joining our presentation. I'm Mohammad Keshavarzi, a PhD candidate at the University of California, Berkeley, and today on behalf of the team, I'll be presenting our work on developing a generative method for populating parametric 3D scan datasets called GenScan. To start, I would like to talk a little bit about our motivation. As you all may have heard, the term 3D deep learning is becoming increasingly trending these days due to its effective application in various research areas, especially in computer vision, in which tasks such as scene completion, semantic segmentation, and mesh reconstruction have all been in a way revolutionized with the integration of 3D deep learning methods. Architecture-related tasks such as synthesizing, completing, and generating novel scenes and layouts have also utilized learning approaches within their process. Yet, like any other learning approach, deep learning is heavily dependent on the learning data that it's provided with. In other words, data is king, and while diverse and high-quality large datasets for 2D images are publicly available for training purposes, 3D datasets are much more limited in terms of size and diversity. In general, there are two types of public datasets out there. First, synthetic datasets, which you can see an example of at left, and second, scan datasets, as illustrated on the right. As you can see on the slide, there can be significant quality differences when comparing these types of datasets. Synthetic scenes cannot always capture the natural transformation and topological properties of objects in real-world settings. Also, the limitations of modeling softwares used for creating synthetic datasets can also introduce unwanted bias to the generated scenes. But when we get down to the numbers, we see a major differences in the size of the datasets. Scale really matters in deep learning techniques, and they often require a large amount of data to be fully trained with. So with this challenge in mind, in this project, we introduced GenScan, a generative method for populating parametric 3D scan datasets. In GenScan, we take a fully scanned building as inputs, and by automating the parameterization of the architectural features of the scan, we output alternative layouts of the same building. In other words, given one single scan, we generate tens of alternative scans using our parametric data augmentation process. Okay, so how do we do this? In the first step, our proposed system extracts the floor plan of the given scan by utilizing FloorNet, a hybrid neural network architecture, which takes point clouds and 2D images from the scan as input and outputs a predicted vectorized floor plan. However, applying transformations on discrete elements of the floor plan can result in inconsistencies. Therefore, we develop and apply a parameterization function to allow wall systems to be continuous and avoid unwanted disconnected spaces. Each line element corresponds to a pair of nodes, and when a transformation is applied to the line elements, the nodes also change position following their corresponding line element. From the floor plan extraction, we can predict locations of the walls and boundary elements of the room. And by applying transformations to the parametric floor plan, its corresponding mesh walls can also parametrically follow the same transformations. However, if we take a closer look, by only moving the wall, we can cause geometrical and topological conflicts with the furniture. And therefore, we develop an additional procedural model for the movement of the furniture clusters. We calculate a bounding box for each mesh cluster, and by assigning the bounding boxes to a corresponding adjacent wall, we are able to move the furniture clusters accordingly and avoid geometrical conflict. Using this process and applying transformations to the floor plan, we are able to generate a wide range of alternative spacings using a single mesh as input. To show examples of the resulting output, we apply our algorithm on real-world scan datasets such as the Matterport 3D, which is captured by the Matterport camera, and also FloorNet, which is scanned using a Google Tango phone. So on the left, you see input scan, and on the right, you see the manipulated alternatives. In addition to the mesh manipulation, our system also generates alternative texture maps for the augmentation process. To do so, we use a pre-trained style transfer technique to incorporate alternative styles into the current texture maps. We also apply various color tints to the transferred texture maps. And applying the new texture maps to the mesh, as you can see in this figure, we can generate a wide range of alternative scan quality geometries and textures from just one single input scan. Okay, to demonstrate how our framework can potentially impact deep learning tasks, we show an example use case of GenScan utilized as a data augmentation technique. In this project of our lab called SceneGen, we develop a contextual generative model for scene augmentation that learns indoor scene relationships from scene graphs extracted from the Matterport 3D dataset. Given a target scene, which can be an AR, the system calculates where an input virtual object should be contextually placed and oriented within a scene. In our performance evaluation experiments of SceneGen, we measure the distance error between our augmented prediction and the ground truth. The experiment process is illustrated in the slide from left to right, where we start from the ground truth scene, we take out a target object, we then feed the incomplete scene to our system as an input and query the best position and orientation of the removed object. Finally, we measure the difference between our calculated arrangement and the ground truth. As you can see in this table, our system outperforms current state-of-the-art systems in nearly all object categories for the scene augmentation tasks. In a follow-up study, we developed a more sophisticated algorithm called GASANet, which combines graph attention, Siamese, and autoencoder networks for our scene augmentation tasks. And this time, we augment the Matterport 3D dataset with GenScan as our data augmentation method. Here's some examples of the bounding box manipulation of the sample rooms of the Matterport 3D dataset via GenScan. We trained our scene augmentation method on the 4 augmented datasets and compared the results. First, a regular Matterport 3D dataset. Second, the augmented Matterport 3D dataset using GenScan. We'll call it here MGS. Third, MGS, which has gone through area checks to make sure there are no rooms with more than 90% open space or significant object collisions. And fourth, MGS with area checks and 4 random object removals taken out one by one. Here we report which dataset achieves the highest performance in the distant error experiment using GASANet. As you can see, when using GenScan as a data augmentation method, the performance of the system can be improved in nearly all object categories. As a conclusion, to summarize our contributions, we developed a generative tool for populating parametric 3D scan models. The system takes a 3D scan as input and outputs alternative layouts and texture maps. The generated data can be used as a data augmentation method for 3D deep learning tasks. The process is fully automatic and can also be manually controlled by a user in the loop. And our experiments show that the GenScan method can improve results of indoor scene synthesis tasks via deep learning. And with this, that's it. Thank you very much for listening, and please feel free to reach out to us with any questions you have. Bye-bye.